Hello, this is Ms. Nichols, and this slideshow is on atoms and materials in our electrostatics unit. The essential question for this video is, what are subatomic particles and how do they behave in different materials? So hopefully in some previous science class you were introduced to the idea of atom and you're pretty familiar with that. There are a bunch of different models for atoms, sort of simple ones and complicated ones. For the purposes of this class, we're mostly going to be using the Bohr atomic model. Understanding orbitals and their orbital geometry will add a level of richness, but also a lot of advanced math to this unit. So for introductory physics, usually we just assume we've got this thing in the middle and these things rotating in little concentric orbits around the outside is the model we're going to be using. And this is the model for the fundamental unit of what's called ordinary matter. Inside these atoms are subatomic particles, and we are always learning about more subatomic particles that exist in the universe, but there are a handful that are the primary ones that we're going to learn about or talk about, focus on in this class. So every subatomic particle inside an atom contains fundamental properties. There are characteristics of these subatomic particles that make them up, including mass, which we've talked about before, lowercase m, measured in kilograms. But the way a physicist thinks about mass is that objects that contain mass create a gravitational field, which we use the letter lowercase g to represent. You've seen that pop up before, Earth's gravitational field, but any object can have a g. Any object that has mass will have its own gravitational field, and consequently, any object with mass will also be experiencing a gravitational force from any other nearby object that has a gravitational field. So it's really the interaction between these two little g's that causes the gravitational force that we experience all the time in our everyday life. We're going to use the same kind of model to represent what's going on with this other fundamental property, which is charge. We will use the letter Q to represent the amount of charge an object contains, and the units for charge are the coulomb, which is a capital C. A coulomb is a lot of charge, so usually we'll be dealing with micro or nano coulombs most of the time, but the fundamental unit is the coulomb. And just like with mass, we would say that an object that has the property of charge is going to create an electric field, and we're going to use a capital E to represent that electric field. And any object that has an electric field will be experiencing this fundamental electric force, or F sub E, from any other object that has an electric field nearby. One note about charge compared to mass is that charge is called, we say that it's quantized. And that means that the smallest piece of charge that we know of, the only thing that really has charge, are electrons and protons. And we can't chop an electron in half to have the charge of half of an electron. We can't have 4.5 electrons in something. We've got to have a whole number of electrons. And so consequently, the smallest possible electric charge on any object is the charge of an electron. And every object must have a whole number of electrons and protons, and that's called quantized. That magnitude of charge is given to you on your AP equation sheet, sometimes represented with a little e. So this is the electron charge magnitude, 1.6 times 10 to the negative 19th coulombs. Of course, mass is not quantized, right? So we can keep dividing things into any ratio of masses as far as we know, and there's no smallest mass. So that's a difference between charge and mass. In this unit, we're going to be dealing with really two subatomic particles most of the time, but I'm going to mention the three most common right now just by way of comparison. Later on in the year when we do duality, we'll talk about a few more subatomic particles, but the primary we're going to be dealing with are protons and electrons. So protons have a mass of 1.67 times 10 to the negative 27th kilograms, and a charge of positive 1.6 times 10 to the negative 19th coulombs. You'll notice that that is exactly the same as the electron charge magnitude. So protons have the same charge as an electron, and we call this positive. And they're relatively large. I know 10 to the negative 27th kilograms doesn't seem large, but it actually is compared to these other subatomic particles. And the other important thing about protons is that most of them are trapped in the nuclei of atoms. There are occasionally free floating protons around, but in general, if they're in a nucleus, you can't get them out without a big problem. So we're going to leave the protons in the nucleus. They don't move around very much. They're pretty much stuck where they are inside their atoms. The other one we're going to be dealing with a lot is an electron, and the mass of the electron is 9.1 times 10 to the negative 31st kilograms. So you'll notice that's like 4 orders of magnitude smaller than a proton, so really tiny. But the charge is still the same as the proton. It's a negative charge, so we have positive and negatively charged objects, and it's negative 1.6 times 10 to the negative 19th coulombs. The other thing to note about electrons is that they can move around a lot. So unlike the protons, they're not trapped anywhere. They can be shared and move from atom to atom all the time, and that's going to be really fundamental to our understanding of electric everything, is that electrons move and protons basically don't. The third big subatomic particle you've probably heard of is the neutron, and just a few things to note about that. It's not going to really come into this unit too often, but it has a mass of almost the same as a proton. It's actually a tiny bit bigger than a proton. It's about 9 times 10 to the negative 31st kilograms bigger than a proton, which is kind of fun. We'll get into that later on. Neutrons are also mostly trapped in the nucleus, and they are neutral. They have 0 charge. So that leads a lot of people to say, why the heck do we even care about them? And again, we'll get more into neutrons later on in the year.
In addition to having charged particles, we could have an entire object that would be charged. But the important thing to note is that we consider electrical charge a quantized variable, which means that you can only add whole electrons or protons or take away whole electrons and protons. You can't put part of an electron or a proton in an object. When you add these protons and electrons, you're going to be changing the overall charge of the object by the quantity of one electron unit of charge, that 1.6 times 10 to the negative 19th coulombs. There is a famous experiment known as Millikan's oil drop experiment, where a scientist shot tiny oil drops through a stream of charged particles, and then they measured the charge of each oil drop. And what they discovered is when they graphed the quantity of charge as a function of basically a bar graph of the oil drops that had that charge, they found this really piecewise function where we're going up in stair steps. And so the conclusion here is that the very smallest stair step, or the quantity of a single stair step, is the charge of one electron or proton, whatever was added to that oil drop, and that you can't have an oil drop that exists in a state in between those two charges, because you can't add or subtract part of an electron or a proton. So overall, if you wanted the charge of an object, it would just be the overall charge of all the protons on that object minus overall charge of the electrons. This is sort of like a sigma q, right? We're talking about the total charge of an object. We really only care about the excess protons or electrons. Most of those things are going to cancel each other out, but there may be objects that have a small net charge by the leftover protons and electrons. Sometimes you'll hear problems that reference point charges. A point charge is an object that has an overall charge, but we're going to assume that that object, the whole charge exists at a single point in space. So this is obviously a physicist's way of simplifying a more complicated scenario. So oftentimes when we're solving charges or problems related to charged objects, we will assume that they are point charges with a q that is equal to the difference between the protons and the electrons. If a problem does not specify that we're talking about a point charge, that means the object has dimension. It exists in space somehow. And objects that have dimension, we have to think a little bit about the distribution of charges on those surfaces. One thing you should know is that if there is excess charge, so if we have an object that has a q that is not 0, a q that indicates either excess protons or excess electrons, those charges are distributed only on the outer surface of the object. The reason why is some calculus-based physics that you'll learn in college. But for now, just know the what, which is that all extra charges only exist on the outside. Conceptually, briefly, it's because, you know, those extra charges are looking for the most elbow room. If you put those excess charges on the inside, they get repelled by too many things because there's too many other atoms around with charges on them. So all the excess charges, whether they're protons or electrons, are going to be on the outside of the object. Here is sort of an image of that. So this is a negatively charged object, and you'll see all the excess electrons are on the outside, nothing in the middle. One other variable that sometimes pops up is big Q. Big Q can be treated similarly to small q in some applications, but the difference is that big Q is specifically the charge stored on a whole plate. So just imagine a big flat piece of metal, and that's going to become really relevant as we move later on. So just realize when you see big Q in an equation, it is specifically charge stored on a plate.
So we've mentioned a few times the fundamental forces, of which so far we are talking about two. We've talked about the gravitational force and the electrical force. And we're going to talk about where they arise from in a future slideshow. But for now, we still need to understand sort of what they do and how they act and how objects experience these. So a reminder that every force in the universe is an interaction between two objects, and these two fundamental forces are no exceptions. So for both of those forces, we've got to have two objects that have the fundamental property to experience the force. And there's a lot of really striking similarities between the equations for Fg and Fe and the way that we notice them in our world, which I'm going to highlight here. And that's a common topic on the AP exam, is to kind of compare and contrast these two forces. In fact, they're so strikingly similar in a lot of their manifestations and a lot of the form of the equation. Albert Einstein actually spent years and years and years trying to unify these two forces because they looked like they really should be somehow able to be combined into a single force, but he was never able to do that, and we still have not. But in any case, what we do know is that both forces, the electric force and the gravitational force, require two objects, and that there is a linear relationship between the amount of each force and the mass and charge of each object. So if you double the mass of one object, the force doubles. If you double the mass of both objects, then the force quadruples because there's two masses in there. And same is going to be true with charge. The other similarity is that both of these forces depend on the distance separating those objects. And more so, it's actually the same mathematical relationship. It's an inverse squared relationship between the force and the distance between the objects. So as the distance between the objects doubles, the force actually becomes smaller by a factor of 1/2 squared, or 1/4. So distance is a big deal here. As distance changes, the force changes pretty dramatically as these things get further apart. Both of these force equations contain what we call a universal constant, so something that we've just measured to very high accuracy to allow us to put these units into a common form, into a common force that that can be used in both of these cases. So for the gravitational force, we use a big G to represent the universal gravitational constant. And this is actually a very tiny value. It's given to you on your AP equation sheet. The value of G is 6.67 times 10 to the negative 11th. You probably won't need to use it in this class. You did in AP1 if you took that, but mostly I want you to know that it has a universal constant and that for G, it's a very small value. For electric force, we use a universal constant called Coulomb's constant, and it's a lowercase k in the equation. Actually, it's a little funky how they show it in the equation, but I'll get to that in a minute. But it's actually a huge value, especially compared to the universal gravitational constant. Coulomb's law is equal to 9 times, or Coulomb's constant is equal to 9 times 10 to the 9th with some big ugly units. You'll see this 1/4 pi E naught situation. Coulomb's constant, it turns out, is connected to another constant that was also established, and so sometimes in equations it's written as a k, and sometimes it's written this other way, 1/4 pi E naught. But either way, the value of that entire thing is 9 times 10 to the 9th. So I tend to think of it as K as a single constant. So here's the equation for Fg. You'll see that Fg is equal to a constant times the mass of object 1 times the mass of object 2 divided by the distance between them. And here's the equation for Fe, which looks very similar. Fe is equal to K, which is the Coulomb's constant, times the charge of object 1 times the charge of object 2 divided by the d squared between them. In your AP equation sheet, it looks slightly different, but it's the same equation. So in the AP equation sheet, it has absolute value of Fe equals, and then instead of the K, it has that big ugly constant, but it's the same thing. It's 9 times 10 to the 9th. And then we have absolute value of our two charged objects, and they have it divided by r squared, representing the radius between those charges, instead of d squared represent the distance, but it's the same thing. So if we had a proton and an electron, they would be experiencing both of those forces because they have both mass and charge. So how would the magnitude or the charge of those forces compare if we're talking about, like, you know, a hydrogen atom where they're located very close together in an atom? Well, the Fg of attraction between those two particles, subatomic particles, in an atom of hydrogen is about 10 to the negative 49th newtons. Now that's a really, really tiny amount of force, but of course they're pretty small particles as well, so it's non-negligible. That is something that we have to take into account when we deal with our subatomic particles, is the gravitational force between them. However, in the same hydrogen atom, if we calculated the electrical force between the proton and the electron, that electrical force is actually going to be 10 to the negative 10th newtons, which is way, way stronger than the gravitational force between them. So what that tells us is that at the subatomic level, typically, the electric force dominates the gravitational force, and that's why it's really important that we understand that particular force between our subatomic particles. So one difference, you saw the similarities on the last slide between those two forces, but one big difference that you're probably already aware of is that the electric force can attract or repel. Gravity only attracts. So gravity can never push two objects apart. There's no anti-gravity or anything of that nature. But for the electric force, it works kind of like a magnet, whereas we can attract or repel using the electric force. If you have two opposite charges, like shown in the top diagram there, they're going to be attracting each other, so opposite charges attract. And if you have like charges, so two negatives or two positives, they will be repelling each other. We use the same equation to calculate the force, it just, the direction of that force is going to depend on whether we are opposite or like charges, and we're just going to go ahead and draw that arrow in the right direction based on our understanding of these rules. One little note about electric force is that it's actually the basis of pretty much all the other forces than gravity that we've used. So we talked about the normal force, we talked about the buoyant force, and we talked about tension and all these other little things. Those actually are all really electric force if you get down to it. Like, so tension in a rope, like, to understand tension in a rope, why does a rope exert tension? You got to go down into the atoms and understand that those atoms are being held together by electricity. The molecules are holding to other molecules in the rope by the electric force. So without this electric force, we'd have no rope. The rope would fall apart and we wouldn't have anything to pull. And same thing goes with the buoyant force and the normal force. Objects in this world are not actually touching each other. You're actually levitating. Your electrons are being repelled by the electrons in the floor, and that's what's actually holding you up. So this thing that we call the normal force is actually just the repulsion between the electrons, the outermost electrons, in two objects that are getting close enough. And that repulsion can push things as we tend to think of normal force being like a physical object pushing, but it's actually the electric force that's pushing. So this is a big deal. Even though we tend to think that gravity is a bigger deal because we see lots of objects falling, in actuality, electric force is impacting everything around us all the time. So as we move through this unit, it is important to understand some properties and characteristics of atoms and their subatomic particles. The first one I'm going to talk about is conduction and what a conductor and an insulator are. So electrical conductivity is basically defined as how easy or difficult it is for electrons to move from one atom to another. It's very similar to thermal conductivity. In fact, objects that have a high thermal conductivity tend to have a high electrical conductivity as well. So like metals and things are highly thermally conductive and also highly electrically conductive. The amount of electrical conductivity an object has is determined by the number of protons in the atom and also just the orbital structure. So that's a little bit complicated. We don't need to have to calculate what it should be. We just need to realize that it's based on some of those orbital properties. There is, people have just measured and calculated the amount of conductivity of different materials, and you'll see on the far right end of increasing conductivity are things we tend to think of as good conductors, metals, and on the other end we have this category called insulators, which are things that it would be very difficult for electrons to move from one atom to the other. So you've probably heard the term insulator before, but we're going to define it as a material that has low electrical conductivity. Colloquially, we could say this is something that you could safely stick in a light socket. This would be because the electrons can't flow through that material and escape and cause problems or damage outside the light socket. The reason materials are insulators is because the nuclei of their atoms are hanging really tightly to all of the electrons. They don't want to give up their electrons, and they don't really want to accept any electrons either. They just want to keep them within the atom. Now these electrons are moving, they're constantly orbiting and spinning around in their atoms, but they can't really escape and move through the material or move off the material easily. This is a very stylized diagram. Obviously atoms aren't square and there's a lot of simplifications here, but if you could look inside an insulator, this is roughly what you would see. Is just each atom contains the appropriate number of protons and the electrons are staying close to that nucleus, close to those protons, and they're not really crossing any kind of boundaries from one atom into the other. Some examples of materials that are insulators: wood, rubber, plastic, etc. All those things would be fine to stick into a light socket. So of course we're going to define a conductor as a material that has a high conductivity, aka something you should not stick into a light socket. For conductors, the atoms are not hanging onto their electrons very tightly. They're happily sharing them between each other, passing them back and forth to different materials. The valence electrons can move anywhere they want in the material. So if this is a neutrally charged conductor, you'll see that the electrons could be anywhere. They're not kind of stuck near their atoms. We still have the same number of electrons and protons in this situation, but they've moved all around. Some examples of conductors: metals are really good conductors. They often talk about the electron cloud in the metals. Water is a good conductor as long as it has any dissolved salts in it. Hot dogs, which of course are very similar to human hands, are also good conductors. So you probably should not stick hot dogs in light sockets because you'll notice that electrons can flow through them pretty easily. Okay, we've reached the end of the video, so take a minute and revisit the essential question, which is what are subatomic particles and how do they behave in different materials? Thanks for watching.